What do you mean by that? We mean that if supposing this is x and fx is an error function, then if its shape is like this, then there is only one minimum. One minimum which is global. So how do we ensure that this the property of the convex function is, let's say we have a point A here and point B here. If I join the function points A and B, then when I move my value from A to B, the function always lie below the line which is connecting FA and FB. So what it is saying that in the interval FA which is the line, because I am interpolating it here. So this is always less equal to you can say come back to 831, or you can say f of then must be, I think. Oh, I'll come back here again. But what I want to say is that this interpolated line should always be less than this is at when p is 0. How come I'm forgetting it? Then the interpolated value of the function when t is varying between a and b. Okay, so if the line lies above it, that means the function always lie below it. So the function behaves like there is only one minimum. Supposing the function is like this, and I join any 2 point on the function with the line, then somewhere the function has a minimum here, function has a minimum here, and the function has a maximum here. So there are multiple optimal points on the function if it is not a convex function. So this is a convex function. And I'll fill this equation later on. I'm just forgetting a simple thing. So what happens is, what we are interested in the error functions in making the neural networks learn is, we are interested in these convex functions because they have only one minimum, one optimal value. Let's call it optimal value, which may be minimum or maximum. So where is the optimal value? When I am changing x anywhere on the function, then there is a change in the error. But if I change x at the bottom, the error is not changing much. It is very infinitesimal. So it is constant here. That is the optimal. So if the derivative of the function can be equated to 0, then I can find a value x which evaluates this f dash at equal to 0. So the derivative of the function gives me the optimal value. And this can be both maximum and minimum. So whether it is maximum or minimum can be determined by double differentiating it and checking the sign. If it is greater than 0, then it is a minimum. And if it is less than 0, then it is a maximum. So this you can actually determine with the help of the closed form solution also. But as I said, in the closed form solution, it is evaluate the X, which is your data, which is huge dimensional. There is large number of data points, and all the data points are high dimensionality. So we need in the optimal solution, it is kind of you need what is y cap is x. If it is x is like this is x1, x2, and xn. So this is 1 by n. And what is your w? W is a vector which is by 1. What you need y cap, which is n by 1. So that's why this x matrix multiplied by w is giving you y cap. So your error becomes y minus y cap whole square. So because this is a vector, the square is done as y minus y cap transpose y minus y cap. Okay? Because अगर आपको करना हो x वेक्टर का स्क्वायर करना होगा तो कैसे होगा x transpose into x. So here when you substitute y cap by xw, so I can write y minus xw transpose y minus xw. Oh, sorry. This is w transpose x transpose to y minus xw. So what I'm saying is if there are two vectors multiplied, xw transpose is equal to w transpose to x transpose. You can check the dimensions. X is n by m, w is m by 1. So the left hand side is n by m. And if I do w transpose, it is and the whole transpose. N by m, and so it is coming n by 1, and the whole transpose is 1 by n. So right hand side is w transpose is 1 by n, x transpose is m by n, 1 by n, and x transpose is n by m. So this will give me 1 by n. So this stands true. Is this okay? Is this okay? Anybody? If you haven't understood it, okay. So I apply this and then I multiply. So what I get? Y transpose Y minus Y transpose XW minus W transpose X transpose Y plus W transpose X transpose XW. So now you know that this is same. Why it is same? Because when we do dot product, we get a scalar value. So if and one is a transpose of another, so the result will be same. If I do a transpose of this, what I get? I get W transpose X transpose Y. So these two values are same. Okay. So I substitute it with Y transpose Y minus 2 W transpose X transpose Y plus W transpose X transpose. So now to optimize it, This is your loss function. You differentiate it with respect to W and equate it to 0. So this does not have any W term in it. So it is minus 2 X transpose W plus it is X transpose X W. So equating it to 0. So, oh, sorry, because it is kind of, this value is kind of W transpose X transpose whole square. So when you differentiate it, you get 2 here. 2, the value W transpose X transpose, so whatever is the value, this is. So equating it to 0 will give you 0 is minus 2 X transpose W plus 2 X transpose X W. So you take it, you can cancel the, there should be somewhere X, Y. Oh yeah, sorry. This is because we have differentiated with respect to W. So ये W term नहीं आएगी, Y आएगी यहाँ. Okay. So now I can write it as 2X transpose X W equal to 2X transpose Y. So 2 and 2 cancels. X transpose X equal to X transpose X into W. Sorry. Oh. To get W optimal, what I have to do, X transpose X. This is a matrix and we have to divide it. We do not have matrix division. So multiply by the inverse of the matrix. So W transpose becomes identity into W transpose equal to X transpose X inverse X transpose X. So W optimal will be X transpose X inverse X transpose. Is this okay? Any question till this derivation? So, okay. So now you know what is the dimension of X transpose. X was n by m. So this is m by n and X was n by m. So this matrix X transpose X, this is so we need at least m independent sample, linearly independent samples in the training data so that the inverse of the metric exists. Otherwise, it is a singular matrix where we cannot have inverse of the matrix. So this might create a problem. And this is a big matrix. So taking its inverse is like division by very, very small numbers. So that may lead to numerical inaccuracies also. So instead of this closed form solution, what we prefer is we prefer iterative solution. Coming back to here, it has to be less equal to f of P of A plus f of 1 minus P of B. So the line that when we are varying t from 0 to 1, then the function value evaluated at that point is always lying below the interpolated line when we are varying t from 0 to 1. When the t is 0, we are at this point. When t is 1, we are at this point, and the function value is as we evaluate onto that. So the interpolated points on the interpolated line, when we choose any 2 points on the line, the function value always lie below that line. It never crosses it more than the intersection points. Then it is a convex function. So now coming back to, we prefer iterative solution. So in the iterative solution, what we say is, while it is time to converge, okay, and we'll see what it is, what is the time to converge. So initially we'll initialize the iteration equal to 1, and we say the learning rate as small value, and we need a threshold, which is you can say threshold error, which is also a small value. So while it is not the time to converge is when the magnitude of your gradient, the gradient of the error function. So gradient of the error function with respect to n is greater or equal to the threshold of the error. Let's write it threshold error. This is also a small one. Okay. So while it is greater than this, we are continuing this. While the magnitude of the gradient of the error with respect to the threshold, the error threshold is greater than, we keep on repeat. Okay. What do we repeat? So first of all, you initialize the weights. Initialize weight. So how do you initialize? You can initialize to 0. You can initialize random. Or if you have some prior information about the domain, then you initialize them intelligently using some method. So what are the various ways to initialize the weights and biases? Zero initialization, random initialization, and of course, by intelligently. So you initialize the weight, you make the iteration as 1, and you make the learning rate as small. So what you do, every point you compute the gradient of the error. You have an error function with respect to weight, update the weight. So how do you update the weight? Update the weight is W, T is 1 initially, the iteration number. So WT plus 1 is the previous weight minus learning rate into gradient of T with respect to. Okay. That is what is your updation. And you make T is T plus 1. This is your gradient descent. Any question about that? Any gradient descent algorithm is like this. What it is saying is, जब तक आपका स्लोप, एरर का स्लोप ज्यादा है, बहुत छोटा नहीं हो गया, तब तक आप रिपीट करिए. आप क्या रिपीट कर रहे हैं? One small step at a time, you proceed in the negative direction of the gradient so that you arrive at the minimum. If you are on the negative side, you keep on adding something into the weight so that they increase. If you are on the positive side, you keep on decreasing till you arrive at the minimum. Now we are keeping this learning rate as very small. The learning rate is a small value. Why? Because if you take it as large, then you might be bouncing around the error surface. And in computer program, there is no inertia, so it won't come down to the minimum. वो थकेगा नहीं तो minimum पे नहीं आएगा, and your algorithm might never converge. And remember, please remember, the small value is something like 0.0001 or something like this. Is this okay? Is this okay? Anybody? Okay. So now what we need is, in finding the minimum, we need this gradient value. What is this gradient? Gradient is when we are taking derivative of a multivariable. Multivariate data. Supposing your function is function over 4-dimensional data. So derivative will be represented as this. It will become a vector. The first value will be partial differentiation of f with respect to x1, partial differentiation of f with respect to x2, x3, and partial differentiation of x with respect to x4. Okay. So when we are computing the gradient of the error with respect to weight, so जितना हमारे पास में weight है, तो error with respect to weight 1, the weights between the two layers. So one, let's say, between weight 1, 2, weight 1, 3, and like this 1D. Is this okay? Hello? This is called gradient. Okay. So now you understand that in gradient descent, what we need is, we need gradient at every node. You remember feed forward back propagation algorithm? Let me come back to that. In feed forward back propagation, what we have done is, we computed the error at the last layer, and from here we have to back propagate this error till the first node and then do the updation of the weights. So let's take an example and try to understand what we will be doing. So the example is, let's say your network is this. So जो मैंने उसमें दिया हुआ भी है, it is, let's say, activation A0, which is your input. It is connected to node A1 with the weight W1, and there is a bias which is let's say B1. This is A1, and let's say A1 is, simplify कर देते हैं, bias भी अभी मिल जाएगा. Then there is W2, you get A2. What is A2? A2 is W2 into A1. Then you have A3. A3 is what? W3 into A2. So the previous input is previous activation is becoming input for the next node. And let's say we have A4, where A4 is W4 into A3. And here we have the final output, so we can compute the cost. When we compute the cost we say is our square function. So the output coming from the last layer is A4, and we are given a y, which is the actual value. So cost is this. So now I can write it here also. A4 minus Y. So to see how this cost is changing when there is a small change in W4. So I want to find out a small change in W4 so that the cost decreases. It decreases by a amount. Even if the amount is small, it has to decrease because my gradient descent algorithm says that you move in that direction so that you change the weight in the negative direction of the gradient with respect to that weight of the function so that it decreases. So here, what I get is if I differentiate the cost with respect to weight, then you know that cost is not a function of weight, cost is a function of A4. So I'll apply chain rule. First, I'll get this, and then A4 is a function of W, so it becomes multiplication of two terms. These are the two terms. All right. So now, if I want to, so when I do the update for W4, the update will be W4 equal to W4 minus whatever is the learning rate into this C with respect to W4. Are we clear here? Hello? Is this okay? किसी को कुछ पूछना है तो आप पूछ सकते हैं. Okay, very good. So now come to the next. इसको मैं हटा देती हूँ यहाँ से. So when now you want to see the effect of W3 onto the cost. So you do partial differentiation of cost with respect to W3. Now, can you tell me what this value will be? So I know that cost is a function of A4 only. So I differentiate with respect to A4. Function of A3. So I differentiate it with respect to A3. And then A3 is the function of W3. So I apply the chain rule and it becomes multiplication of three terms, where two of these terms are coming from the node which is after this. So this is called upstream gradient. And this is the local gradient at this node, which I am differentiating this node with respect to its input. So this is the local gradient. And now this complete will become upstream gradient for the next node. So let's see how it becomes upstream gradient for the next node. If I want to see the effect of change in W2 onto the cost, what it will be? It will be partial differentiation of cost. It is a function of A4. A4 is a function of A3. A3 is a function of A2, while A2 is the function of W2. So you know all these three terms, these are the common terms which are coming from, and these are the local gradients. So the upstream gradient multiplied by the local gradient. Finally, when you want to check the effect of the first weight, it will be A4, A4 with respect to A3, A3 with respect to A2, A2 with respect to A1, and A1 with respect to. Is this okay? So what is now the let's find the values. ये डायग्राम देखते हुए बताइए if I differentiate A1 with respect to W1, A1 is W1 dot A0. So what will I get? Anybody? In the diagram, you know A1 is W1 A0. So when I am differentiating A1 with respect to W1, what should I get? भाई ये तो बताना पड़ेगा ना. A1 is W1 A0. If I differentiate A1 with respect to W1, what should I get? Answer to A0. Yes, very good. Very good. So यहाँ I'll get A0. If I differentiate A2 with respect to A1, then what do I get? A2 with respect to A1. So A2 is A2 equal to W2 into A1. So when I am differentiating A2 with respect to A1, I will be getting what? No, I am differentiating with respect to A1. And A2 is W2. Yeah, W. So I'll get W2 here. Then I am differentiating A3 with respect to A2. So what will I get? W3. Then I am differentiating A4 with respect to A3. So I'll get W4. And finally, the cost with respect to A4, which is 2 into A0 minus Y. Is this okay? Is this okay? So you see, जो लास्ट में जो डेल आया था, वो डेल जो बीच में इंटरकनेक्टेड नोड है उनके प्रोपोर्शनल में W4 टाइम्स कहीं A4 A3 में W2 है या W3 है. यहाँ पे 4 है. W4 W3 W2 and A0. So finally, you know, जो अपन ने फीड फॉरवर्ड बैक प्रोपगेशन में करा था, उसमें अपन ने क्या किया था कि जो एरर बैक प्रोपगेट हो रहा है वो क्या आ रहा है? Whatever is the error, it is back propagated the weight times जो upstream gradient है times the weight, and then ये इसके local gradient से multiply हो रहा है, that becomes the error. It gets multiplied by the weight which is connecting the previous node to the next node, and this gradient, the error del function, and this gets propagated back, and then we do the updation of the weight. So this is called back propagation of. Is this okay? Any question? Any question regarding this? अपना नो ये ठीक है आपको? ये चीज समझ में आ गई? हेलो. Yes. Okay. So now I come to the slides I was taking. Where is that? No. Sorry. तो इसको अपन समझ सकते हैं. एक बहुत ही अच्छा टूल है which is functional diagram. What is the functional diagram is, we have a function f and it has certain inputs. What is the job? Let's call this a node as the node in the neural network. So what this node job is, we are representing a node with the help of a functional diagram. in the functional diagram, a node has certain inputs and there are outputs. So what is the job of the node is to apply the function that is specified in the node onto the input and give out the output. So this is kind of feed forward step. So if the input is X and Y and the function is plus, then what it will do, it will give me, it will give me X plus Y as output. Okay, so if it is plus, so Z will be equal to X plus Y. So this is the forward step. And what is the backward step? Backward step is it has input as the upstream gradients. What it does is it computes the local gradient and multiplies them with the upstream gradient and pass them as input to the input nodes. So आपके पास में यहाँ पे इनपुट क्या है? इनपुट दो हैं, एक x है, एक y है, और यहाँ पे ये आउटपुट क्या था? z था. तो जो आपके पास में अपस्ट्रीम ग्रेडियंट आएगा वो लॉस डिफरेंशिएटेड विद रिस्पेक्ट टू दिस इनपुट z, so which is partial L over partial z. लोकल ग्रेडियंट क्या होंगे? लोकल ग्रेडियंट विल बी partial z is the output z, partial x for x and partial z or partial y for the y direction. So जो आपके पास में डाउनस्ट्रीम ग्रेडियंट जाएंगे वो क्या जाएंगे? This upstream gradient multiplied by this local downstream gradient which goes as like this. So this is partial L over partial x. It is the chain rule is getting applied. L is a function of z, so you differentiate L with respect to z. Then z is a function of x, so you multiply it with the partial differentiation of z with respect to x. For y also, because L is not a function of y, so L is a function of z. So you take a partial differentiation which is coming from upstream gradients. You multiply it with the local gradient partial differentiation of z with respect to y. So the job of the functional node is that it will multiply the input, it will apply the function onto the input, give a output. What it does for the back propagation, it gets upstream gradients and multiplies with the local gradients and pass them as output onto the input. Is this function clear to you? In terms of the functional diagram, is this clear? Or you have any question? Yes, it is. So let's say this is an example of applying the chain rule. We know that. Now we'll try to solve certain things and to see how the functional diagram help us in understanding feed forward and back propagation. So forward step is what? Forward step is simple. Given input n, you compute fn and give as output. What is the backward step? Given backward input, which is the upstream gradient. So it is, we are getting from the node which is output for us. What we return this upstream gradient multiplied with the local gradient of f with respect to n. Hope it is clear. So the output is specified as forward arrows with the blue color, and the backstream gradients are specified by red arrows which are facing backward. This is our functional node. So let's say, and as I said, what are these nodes? These nodes are nothing but they carry some numerical values. So it is just flowing of numbers from the input to the output. And again, there is flowing of numbers from the output to the input. Now let's say your function is minus x plus 3 whole square. So what I am doing is I am first of all encoding a node for doing whatever is input, I just negate it. So this is a node which is doing that job. Then whatever is the input, I add 3 to it. Then there is another node which is doing the square operation. Is this okay? I break this down, this function minus x plus 3 whole square into 3 nodes. First, whatever is the input, it will be negated. Then the output is minus of that input. Then there is a node which adds 3 to it. So output becomes minus x plus 3. And now I do a square. So the output is minus x plus 3 ka whole square. So this is the output here. Okay. Now let's say at the last layer, the gradient is with respect to the output. So the gradient always remains 1. So when the gradient is 1 here, now my node is n square here, and I have to do local differentiation here. What is the local differentiation of n square? It is 2n. And what was the input here? The input was minus x plus 3. So differentiation is 2n, and I know n इसका input क्या था? इसका input था minus x plus 3. So the downstream gradient will be 1 into minus x plus. Is this okay? Sorry, 2 into. So when you differentiate n square, you get 2n. Is this all right? Now the upstream gradient that is coming is minus 2x plus 6. And when what is the local gradient? When you have something as x plus y and the function is, sorry. And if I differentiate it with respect to x, then I get 1. If I differentiate it with respect, so I get 1. So the local gradient is 1. So this gets passed on as it is as 2 minus 2x plus, and here the local gradient is will be minus 1, so it will be multiplied and you will get 2x minus 6. You are getting? So you understand it now? And plus 6, which is further multiplied by the local gradient, which is 1. Then it is multiplied by the local gradient, which is minus 1. So you get this output. This clear, or should I explain it again? Clear. Okay, very good. Now we understand how these gates are behaving. Supposing we have a adder gate, as I told you, कि अगर मेरे पास में कोई x plus y करना है, तो मैं इसको जब डिफरेंशिएट करूंगी विद रिस्पेक्ट टू x, तो मेरे पास में क्या आएगा 1. And I differentiate it with respect to y, then also I get a gradient. So when there is a adder gate, the differentiation is always 1. So whatever upstream gradient is coming, it gets distributed equally onto the downstream nodes. Okay. When I have a multiplier gate, so for example, f is x into y. So if I differentiate it with respect to x, I'll get a y. If I differentiate it with respect to y, I get a x. So what it does is, when the upstream gradient is coming, it is getting multiplied. These values, जो इसका input था, they get swapped. जब when I am x के ऊपर क्या जाएगा, y जाएगा, और y के ऊपर क्या जाएगा, x जाएगा. तो यहाँ पे इस मल्टीप्लायर गेट को आप ध्यान से देखिए. यहाँ पे आपके पास में क्या हो रहा है, upstream gradient is 5. So 5 जब ये, let's say this is x and this is y. So 5 multiplied with the local gradient with respect to x, तो वो क्या आएगा, y. इसलिए 5 into 3 is 15 here. And 5 will be multiplied by the local gradient of this 3 into 2 with respect to 2. So वो आपके पास में 3, तो which is y, so which will be 2 into 5. So a multiplier gate, when it gives the downstream gradients, the multiplication is that the inputs are swapped. If it is multiplied, it is swapped, and then it is multiplied by the upstream gradient and given as output. Is this okay? Hello? Right? It is okay? And then there is a copy gate. So copy gate does nothing, but it just copies the upstream gradient, the sum of the upstream gradient as downstream gradients. We are doing nothing, केवल उसको copy करना है. There is a max gate. What max gate does is ये output क्या देगा, जो भी maximum value होगी. जैसे यहाँ पे 4 and 5 था, तो output is 5. And when there is a gradient which is to be passed down, that means only one of the path was active because it is a max gate. So this gradient will be passed down towards that path. Is this okay? So these are the rules that we apply onto the functional graph. So let's do it one more times with the help of numbers. So because earlier अपन ने उसको as the equation किया है, जो आपके पास में जो नोट्स बने हुए हैं, नेटवर्क बना हुआ है, उसमें इक्वेशन कुछ नहीं है, वहां तो केवल नंबर्स हैं. So now let's say you have a functionality x plus y into z. So I break it into two nodes. X plus y is one node, and then multiplying it with z is another node. So I make a node which does, it adds any two numbers given to it. Then there is another node which is a multiplier node. It adds the values which are input to it. So if x is 1 and y is 4, then the output will be 5. And if supposing z is 10, then the output will be n into m equal to 50. Is this okay? As if it is a feed forward network. Now batch propagation kaise hoga? The upstream gradient at the last node is 1. Now let's complete. There are two paths. एक 5 इनपुट आ रहा है, एक आपके पास में 10 इनपुट आ रहा है. तो मुझे बताइए कि यहां से डाउनस्ट्रीम ग्रेडियंट क्या निकलेंगे. This is a multiplier node. So downstream gradient on 10 के ऊपर क्या निकलेगा? Upstream gradient is 1. So 1 is multiplied by anyone? 5. Yes, very good. And यहाँ पे क्या आएगा? It is 1 is getting multiplied by 10. So that's what is happening here. So 5 comes as a downstream gradient here. 10 goes a downstream gradient here. It is a adder node. We know that the local gradients are 1. So the 10 is passed in both the directions as the downstream gradient. We are good. Now let's come here, a bit more complicated. So we have the expression as 1 over 1 plus e raised to power minus. Why I'm showing you this? Because we know that we have sigmoid as activation function in the hidden layers. So how do we solve that? I'm breaking it into the simplistic nodes. W naught into X naught, I have one multiplier node. W1 into X1, I have another multiplier node. Then I add these two. So this is a sum. There is a typo error here. This should go here. So this is added with W2. So we come here. Now, because it is -1, so I have a node which is multiplying the whole value into -1. Now this is raised to power e, so it is e raised to power n. Then 1 is added to it, so 1 is added to it, and the whole is 1 by n. So you understand the functional graph for this expression? Very good. So let's solve it. So let's say we are given values as W naught is 2 and X naught as 1. So दोनों को multiply करेंगे तो output क्या आएगा? -2. Now W1 is -3 and X1 is -2. So you get output as 6. It is an adder node. So you do 6 -2, you get a 4 output. And now there is an input, another adder gate with input as 4 and -3. So you get output as 1. There is a multiplier gate with -1. So the output becomes -1. Now there is e raised to power -1. So e raised to power -1 is 0.37. So output is 0.37. You add 1 to it, so the output is 1.37. Now you do a reciprocal of 1 over 1.37 and the output is 0.73. Is the forward pass clear? Forward pass clear? Yes. So backward pass में, now you will give me the first downstream gradient is 1. यहां से क्या निकलेगा ये जरा कंप्यूट करके लिखिए. यस, एनीवन? देखिए यहाँ पे क्या आएगा आपके पास में 1 ओवर एन है. सो 1 ओवर एन का डेरिवेटिव क्या होगा? एफ एन इज एन रेज टू पावर -1. जब इसका डेरिवेटिव लेंगे तो क्या आएगा? -1 इंटू n-2. सो इट इज काइंड ऑफ -1 ओवर एन स्क्वायर. अब निकाल सकते हैं आप. और n की वैल्यू क्या है जो यहाँ पे इनपुट थी? 1.37. या वेरी गुड. किसने किया है? कुमार भास्कर. वेरी गुड. So Bhaskar, now n, which is the input here. So now what is the value which will be coming out of this? कंप्यूट करके बताओ ना. -1 डिवाइडेड बाई 1.37 का होल स्क्वायर क्या आ रहा है? नहीं कर रहे? ओके. So this is, you get it here, it is -0.53. Yes, यहाँ आपने निकाल भी लिया. This is clear to everyone? Now there is a adder gate and we know the adder gate, the derivative is 1. So this will be passed as it is. यहाँ पे -0.53, इधर भी आपके पास में -0.53 आएगा जो कि यहाँ पे आ रहा है. Now your local gradient, we have to compute gradient of e raised to power n. So gradient of e raised to power n is e raised to power n. So you compute e raised to power n. N is what? -1. So ये compute करके बताइए क्या वैल्यू आ रही है? तो लोकल ग्रेडियंट हो जाएगा e raised to power -1 into 0.53, which is -0.2. So here you will get a -0.2. Now it is multiplied by -1. तो आपके पास में मल्टीप्लीकेशन के अंदर केवल it is a constant multiplied by -1. So the derivative is again -1. So it should be output as 2. Okay. Now there is a add gate and we know that the derivative will be distributed equally to both the sides. तो यहाँ पे 0.2 आ जाएगा, इधर भी 0.2 आ जाएगा, which is shown here. Yeah. Then again there is a adder gate. So the derivative is distributed as it is 2 and 2. नाउ इट इज अ मल्टीप्लायर गेट, तो यहाँ पे क्या आना चाहिए, यहाँ पे आना चाहिए दिस अपस्ट्रीम ग्रेडियंट इंटू -1, सो -1 इंटू 0.2 आएगा, और यहाँ पे क्या आएगा 2 इंटू 0.2. Similarly here it will be 0.2 into 3, and here it will be -2 into 0.2. So you check it here. This is what is happening. So this is the final answer. Do you understand it? Is this clear? So now, instead of writing this whole complicated block, I can substitute it with the sigmoid function. Why? Because derivative of sigmoid is very simple, which is, you know how to compute derivative of a sigmoid. जब डेरिवेटिव निकालेंगे तो क्या होगा, 1 प्लस ई रेज़ टू पावर -x. सो ये क्या हो जाएगा, -1 to 1 प्लस ई रेज़ टू पावर -x -2 इंटू ई रेज़ टू पावर -x, एंड -x का डेरिवेटिव क्या आ जाएगा, -1. सो -1 प्लस हो जाएगा, it will be e raised to power -x divided by 1 plus e raised to power -x का whole square. So which is equal to e raised to power x 1 plus e raised to power -x into 1 over 1 plus e raised to power -x. ये चीज क्या है, this is your sigmoid, and this portion is, if I do 1 minus sigmoid, what I get is 1 plus e raised to power -x minus 1, which is equal to e raised to power -x 1 plus e raised to power -x. That's why, as I said, we use the sigmoid as it is in the block, because we know its derivative is whatever is the value into 1 minus the value. And you please solve this with this given values and try to find out an answer. Is this clear? Is this clear? So I hope you have understood feed forward back propagation algorithm, which is used in deep learning extensively. Wherever you are learning from the features, you are training the network, you find in every deep learning architecture, you find a fully connected layer. What is that fully connected layer? This is the deep neural network where you are doing the learning. So कल अपन ने देखा था वेनिशिंग ग्रेडियंट प्रॉब्लम, तो वो किस में होती है, सिग्मॉइड में होती है. तो यूजुअली सिग्मॉइड इज नॉट यूज्ड एज अ हिडन लेयर एक्टिवेशन फंक्शन. It is used as an output when we are doing binary classification. For hidden layer, the activation function which is preferred is the ReLU activation function, and there are various variants of ReLU. And ReLU mein why? Because the derivative is 1, so it becomes easier. Now I'll again like to come here, जो मैंने एक convex function का बताया था आपको, ये यहाँ पे सॉरी मैं इसको करेक्ट करना चाहूंगी. What I want to say here is a function is convex function if you interpolate the values from, let's say, a to b. Then the function evaluated on the interpolated value. So t times a plus 1 minus t times b. ये लेट्स से यहाँ पे वैल्यू है, तो इस पे जो फंक्शन वैल्यू इवेलुएट हुई वो ये यहाँ पे हुई, which will always lie below the interpolation of the function values from A to B. So the interpolation of the function values from A to B is this left hand side equation T FA plus 1 minus T FB. It always will be less than equal to, let me write it correctly. I'm sorry, वहां पे थोड़ा सा मुझे एक challenge आया था, but it is clear now. So TA plus 1 minus TB. Okay, and T is lying between 0 and 1. So this is the property of the convex function. That's why we always prefer convex functions as our loss functions. Why? Because they have only one optimal value, which if it is a concave function ऐसा, तो ये optimal value hill climbing हो जाएगा. Hill climbing में instead of gradient descent, it is gradient ascent. Gradient ascent में क्या है? Here the gradient is positive, here also it is positive. So weight updation आप क्या करते हैं? I plus 1 is Wi, small step in the direction of the gradient instead of in the negative direction of the gradient, because you want to go at the top. And where is the top? Where the derivative is equal to 0. And whether it is maximum or minimum, you take the second order derivative and you check its sign. If it is negative, then it is maximum. If it is positive, then it is minimum. I hope it is clear. Any questions? Hello. So Vikas, I think it is okay now. I'm so sorry, मुझे थोड़ा late पता चला कि I have a class and then. Hello Vikas. Okay, so Dr. Surinder is there. Okay. So this is fine?
Yes, okay.
Okay, okay.
Thank you.
So thank you so much. Thank you everybody. I can exit now.
Yes, yes.
हाँ महिपाल. हाँ बस आ रही हूँ. वो एक्चुअली विकास ने क्लास रखी थी, मुझे पता ही नहीं थी. ओके, आ रही हूँ, आ रही हूँ. मैंने वो देखा नहीं, मुझे लगा कि कल का एक्सटेंडेड था, वो आज वो बोल रहा था नेक्स्ट पे लगा था. फिर मैंने देखा टाइम टेबल में, मैंने कहा 1 टाइम तो वो था तो क्लास का ही लेक्चर, तो मैंने कल